Hello everyone, so welcome back to our latest session. So until now we have been discussing the fundamental aspects and what are they, I guess, equilibrium and kinetics, right? Equilibrium gives us an idea about how far can the system travel, let's say, and kinetics will give us an idea about how fast will the system go, right? So we discussed the relevant aspects in great detail. So now we are done with the fundamentals. We are going to move on to the applications, and let's look at what they are in general before moving on into greater detail into one of these aspects, which is going to be acid and base reactions, right? So the bigger picture here is that we looked at equilibrium and we looked at kinetics, right? How far and how fast, and we are done with these two aspects, right? And now we are going to look at the applications, and what are the usual applications we come across as environmental engineers, I guess, are acid base reactions. We come across complex formation or formation of complexes, and we also come across precipitation or the dissolution of the relevant solid, and more importantly we will look at redox process 2 or the oxidation and reduction process, right? So these are what we are going to look at. So in each of these cases we are going to look at the effects of equilibrium and kinetics in each of these cases, right? So acids and bases are an important aspect with respect to environmental engineering. Why is that? We are going to look at that in the next couple of slides. So I guess first, acid base reactions is our major heading here, our major topic of discussion. So we are going to talk about the importance, right? So what's the importance, I guess, right? Let's look at the relevance. We always need to look at the relevance. Why do we need to discuss what it is we are discussing now? Why talk about acid base reactions now, right? So in general, let's say in the lab, let's say, I'm mixing two solutions, I have two beakers, I mix them up, right? And I want to know what is the final pH, a simple example, I guess. Again, what do I need to look at? The relevant acid base reactions, right? For example, though, if I am looking at the common effluent treatment plant, let's say, right? And here you have, let's say 150 or 100 industries or greater than 100 industries dumping their waste to this effluent treatment plant, right? You have different kinds of wastes with different volumes. So volumes are different and the characteristics are different, right? So you might end up with a pH that's relatively abnormal, let's say, right? And you want to neutralize that before you either send it to biological treatment, right? And so on. So how do I look at these or how do I go about neutralizing this particular wastewater that has constituents from different kinds of industrial waste, right? So I need to look at the relevant aspects like alkalinity, certainly, acidity, which I guess is relatively what do we say, determined, or is correlates, not correlates, I guess. You can understand in the context of alkalinity itself, so I will not go further here. So you need to look at alkalinity and acidity and so on, and then look at the amount of acid or base that needs to be put in to be able to neutralize your particular wastewater. So that's one particular example there. So another example you can look at is, let's say you have pipes, let's say, right? And in general you have either copper or lead pipes. I'm talking about distribution pipes, not maybe widely in India though, copper or lead. So if you want to avoid corrosion, you are going to have corrosion due to chemical process. You want to avoid corrosion, you can maintain a specific pH, right? Either to what do we say, form a protective layer above this particular surface, right? If there is certain alkalinity in your particular system, you can form a protective layer with the calcium carbonate precipitate. For that you need to look at the pH, or by adjusting the pH itself you can, what do we say, lessen the kinetics with respect to the corrosion of copper and lead, right? This is one other practical example. So other aspects is that, let's say that pH affects your treatment efficiency of various unit process, right? So, how is my pH going to affect various treatment or unit process like let us say coagulation and flocculation, let us say, right, or heavy metal removal. How do I remove heavy metals in general? How do we remove them? Let us say we try to form precipitates, or we try to precipitate them out, you know, with either OH minus as a ligand or any other ligands, I guess, that you either add or are existing in solution. So, for that, what is the critical aspect now? It is going to be pH, right. So, that is another aspect that you need to look into, yes. So, again, what else? Let us look at acid rain now, something that people look at, let us say. So, under what conditions or such will acid rain be formed, right, of sulfur dioxide, let us say, or what concentrations are required, let us say, and let us say if this particular acid rain falls on a particular lake, what is going to be the effect of that particular acid rain on the particular lake, what is it going to be? So, that is something that I need to look at, right. So, and again let us say I have two wastewaters that I am mixing now, wastewater 1 and wastewater 2, right, and now I have let us say different alkalinities for both the cases and different kinds of ligands for both the wastewaters, right. So, now I have a mixture, wastewater mixture. So, how are these particular variables, which are again going to be dependent upon the pH of the system, right, going to affect my heavy metal removal? This is another aspect obviously again that I need to look at, right. Again the key aspect here is pH or obviously acid base reactions again, right. And let us look at one other aspect. So, let us say you have a contaminated soil, right, with heavy metals, and let us say, you know, again this is the surface of your soil or earth, and this let us say soil, please excuse my poor drawing skills, and this let us say is my soil, and let us say I have a precipitate of various heavy metals here, right. So, for now let us say if it is precipitated out, it is relatively immobile though, right, and this let us say is the groundwater table, okay. And for now we have precipitates and they are immobile, right, and you do not want them to contaminate your groundwater. But let us say if it comes in contact with relatively acidic pH water, let us say, what is going to happen now? In general, depending upon the kind of contaminant, I guess, there can be dissolution now, right, depending on the pH of the water that it comes in contact with, there can be dissolution, and then that can leach again into the groundwater and again contaminate the groundwater, right. If this is the groundwater flow direction, you are going to have a contaminated plume, right. So, again what is the important aspect here? pH or acid base reactions would determine the mobility of your precipitates, let us say, or contaminant. I guess a better word in this context would be a contaminant, right. So, that is one particular case. Let us look at the last aspect maybe. What else can I look at? Let us say, okay, let us say there is rainfall, let us say again, right, and I will try to relate that to this particular extent here, example here, and this is my soil, right, and for example it comes in contact with rainfall, and let us say the pH of that rain droplet is a particular value, right, and this will be after equilibrium with your particular constituents in the air, right. You will have again acid base transformations here, right, and again you will have calcium carbonate, let us say, as a deposit in your particular soil, and now you are again going to have acid base interactions here, right, and again you would want to then be able to calculate what is the final pH of this particular soil here. Once you take into consideration the interactions between the relevant constituents in the gaseous phase with the water droplet, and then with the water droplet again once it comes in contact with the lime or calcium carbonate deposits, in the subsurface, right. Again, what are we concerned with again? Acid base reactions, right. So again, the importance of acid base reactions is ubiquitous, right. Even in our gut, right, the stomach, I guess, right, you know, there is a specific pH that's maintained in the gut, either to propagate the growth of specific bacterial colonies or to restrict the growth of certain species of microbes, let's say, right. So again, the whole body or the system that we look at in nature is going to be dependent upon acid base or pH reactions, yes. So let's go through and look at what we have later. So again, here we have terminology, and we are going to look at two ways to understand or define what a acid is or what a base is, right. Here we have acid and here we have base, yes, and let us see what we are going to look at, let us see. So here we have Bronsted-Lowry theory. So this is applicable in general to aqueous solutions, right. It is applicable to aqueous solutions, yes. So how do we define that? Let us say we define acid as a proton H plus or a proton donor, right. And how do we define a base as? Obviously the inverse, H plus or proton acceptor. So an example will be HCl, an acid. I add it to water at relatively neutral pH or at most pH, it will dissociate into H plus and Cl minus. So as you see, HCl is donating a proton, right. So I would say HCl is an acid, yes. And here with respect to base, one usual example obviously is sodium hydroxide. If I add crystals of sodium hydroxide to water, let us say, what is going to happen here? So it is going to release Na plus plus OH minus, and OH minus again, what will that do? OH minus will consume the H plus in my particular solution and go to H2O. So in effect it means that it is going to consume or accept a proton, right. So that is what we say here, or you can even call a donor of the OH minus, I guess, right. So again, let us clear up what we have. Whenever you have a particular compound releasing protons or a proton donor, we call that a acid, and whenever it is accepting a proton, we say that is a base, right. So this is for your basic knowledge, I guess. But in general, thus as we talked about is only applicable in your aqueous solutions, right. So let us look at a wider, more widely accepted, right, theory, that is the Lewis based definition of acid and base, which is not only applicable to aqueous solutions, but even when you have solvents and such involved, right. So or you know, this is applicable to non-aqueous solutions too. So with the Bronsted-Lowry theory, you will only be able to explain a bit of or a few acids and bases, but the Lewis will give you a bigger set, right. So more or less Bronsted-Lowry definition will give you a subset of the Lewis acids and bases. So again, what is a Lewis acid, I guess, right. We are going to say it is going to be a non-bonding electron pair acceptor. So it is an acid is one which would accept a pair of non-bonding electrons, and same case base non-bonding electron pair donor, right. So acid is one that will accept a pair of electrons, right, and base is one that would donate a pair of electrons, a non-bonding pair again, right. So this is one example, I guess. So we are going to usually be concerned, at least in this class, with the Bronsted and Lowry, because we are mostly going to look at non-aqueous or aqueous solutions, pardon me, or with water as the solvent. So when we have non-aqueous solutions, you can look at Lewis theory, and that is the generic what do you say definition here. So we can look at one example here, and that is ferric H2O and 6 and 3 plus. So that is going to dissociate into Fe H2O 5, and what else if it is going to dissociate OH 2 plus H plus. So in effect the Fe or ferric is pulling electrons from H2O and thereby releasing H plus, right. So, it is an acid here. Why is that? It is pulling the electrons from water. So, it is a electron pair acceptor, and that is why you can call this particular compound here or complex here to be a acid, right, and this is one particular example. So, we do not need to go into that in greater detail though. So, moving on, what do we see here, guys? We see that pH is a master variable, and what does that mean? It means that in the context of almost all inorganic interactions, let us say, or most other systems or engineered systems, pH as a key variable or the master variable, especially with respect to inorganic interactions and most of our engineered systems. pH or the relevant acid base reactions are going to be the key. So, right, and now we are going to talk about kinetics in the context of acid base. Yes. So, in general, the half life of the acid base reactions are typically less than 1 millisecond, let us say, right. So, the kinetics is relatively fast or remarkably fast in general. So, what does that mean now? So, for all practical purposes, the characteristic time or the time that we look at with respect to our systems is much greater than the reaction time or the half lives here. So, right, what does that mean? It in effect means that the kinetics are so fast that the system will almost always end up reaching equilibrium, right. So, that is what we are talking about. So, what does this mean? So, we do not need to look at kinetics in general with respect to your acid and base reactions, right. Why is that? Because the kinetics are so fast that for most of your characteristic times you will end up reaching equilibrium. Yes. So, what are we going to do? We are going to talk about equilibrium in greater detail from the throughout acids and bases, I guess. And again, the reason is that kinetics are so fast that we can more or less neglect that, and almost always equilibrium is reached by the time you try to look at your system or analyze the system, right. So, here we are going to look at a single dissociation reaction. Let us say I have an example of HA, let us say an example, I guess, hypothetical example here, and that can dissociate it into its conjugate base, let us say, pardon me, right, and HA and A minus, this pair we call that a conjugate acid and the conjugate base, right. So, let me just clear this up, I guess, H plus and A minus. So, examples, I guess there are many. HCl can go to H plus and Cl minus, right, or you can have this has only one proton to donate, or I can have H2SO4 and that can dissociate into H plus and HSO4 minus, right, and HSO4 minus can again dissociate into H plus and SO4 2 minus, right. So, more or less the net reaction would be something like H2SO4 can give out 2 protons, depends on the pH, we will look at that in great detail later on, and SO4 2 minus, and various examples of acids that we come across usually are H2CO3, right, and HNO3, the nitric acid, right, HCl, H2SO4, H2CO3, nitric acid, and in general in wastewater you come across CH3COOH, the acetic acid. So, we will talk about that in greater detail later on. So, what is this Henderson-Hasselbalch equation about, I guess? So, let us see what it is first, and then we are going to try to derive that. So, this will give me an idea about how the pH, right, would define the concentration of the conjugate base and the acid. So, let us try to derive that. So, for that particular case we are going to look at a hypothetical acid dissociation. So, the acid here on the left hand side is dissociating into H plus and its conjugate base, that is what we have represent here, right. So, here let us say, and from our equilibrium equation we know that the equilibrium constant is going to be activity of H plus times activity of A minus, right, by activity of HA. Again, this is from our equilibrium equations, and what is that, I guess, right? This is the equilibrium constant. But for acid and base reactions, we typically call the equilibrium constant as the acid dissociation constant. So, acid and base, so you see that the acid is dissociating into H plus and A minus. So, the relevant equilibrium constant is called the acid dissociation constant, and that is a term we are going to use with respect to our acid and base systems, right. So, here we have Ka is equal to the activity of H plus into activity of A minus by activity of Ha. So, right, I am trying to get a relationship between pH and the ratio of these two or these variables here. So, obviously, as we know, pH is equal to the negative logarithm of activity of H plus. And how can you in general measure the pH? You have an electrode with a standard electrode or a pH meter. Principle being, it will have a standard electrode or a reference electrode, and you will give or you will let the machine know what the potential difference is at various known pH values, pH 3, 7 and let us say 9, right, and the machine then can calibrate and then measure the pH of your particular solution. Anyway, we digress there. So, coming back to what we are looking at. So, for Ha dissociating into H plus and A minus, we have the acid dissociation constant. This is a constant for that particular reaction, obviously, right, or the equilibrium constant for this case, activity of H plus into activity of A minus by activity of the acid. So, because I want to get at pH, which is negative log activity of H plus, right. So, I am going to take the logarithm of this function. So, what is that going to be? Log of Ka is equal to log H plus log of activity of the deprotonated form by activity of Ha, right. That is what we have here. So, here I am going to have I am going to swap these two variables. So, minus log H plus is equal to minus log Ka plus log activity of A minus by activity of Ha, right, and this is what we have. So, what is this particular term here? As we know, that is equal to log activity, pardon me here, I am missing the terms here, right, activity of H plus as we know is pH. So, pH, and similarly we call or we are going to represent minus log Ka as pKa, right, and this is something you are going to keep in mind, or that is going to be remarkably important in your acid and base systems, plus log A minus by Ha, right. So, this is the Henderson-Hasselbalch equation. And this is remarkably important. Why is that? Because it tells you at a given pH, right, what is the ratio of your conjugate base and the acid. Why is that? Because now you want to, let us say, look at, I want to get a solution to a particular pH, let us say. I want to know the amount of acid that I need to put in to be able to get to that pH, right. So, depending on the choice of the pH, the acid, and the current pH of the system. So, choice of the acid means depending on the pKa and current pH, you are going to only have a release of certain amount of H plus, right. So, for that particular case, you are always going to look at the Henderson-Hasselbalch equation, yes. So, what does this mean though? So, it means that if pH is equal to pKa, right, what does that mean? The activity of the conjugate or deprotonated form is going to be equal to the activity of your acid, and if I am going to approximate it by concentrations, it is going to be A minus and Ha, yes, and if pH is greater than pKa, right, what does that mean? It means the log of activity of A minus by activity of Ha is greater than 0. What does that mean? It means the concentration or activity of A minus is going to be greater than concentration of HA. And same case, if pH is less than pKa, this particular variable is going to be less than 0. And what does that mean? The concentration of the conjugate base is going to be less than the concentration of the acid, right. So, with that I will end today's session. So, let us just have a brief review, I guess, right. So, we have looked at the importance of acids and bases both in natural and engineered systems, and then we looked at two particular definitions of acids and bases, and they are Bronsted-Lowry and Lewis. This is applicable in aqueous, and thus is something that we are going to use widely throughout the class, and thus Lewis theory is applicable in non-aqueous solutions, right. And then we came across the Henderson-Hasselbalch equation, and we looked at new terms pKa, which is more or less minus log Ka, and what is Ka? The acid dissociation constant. So, pKa will give you an idea about how strong or weak is the relevant acid, right. So, we will discuss this in the next class, and for this session that is it from me, and thank you.